So correlative coding is a type of encoding your message signal whenever you have continuous ones or continuous zeros, and you are trying to uh, allow a controlled amount of what do you call ISI, right? So we consider that on the left hand side, we can see there are two ones being sent in the rectangular format, right? So one, right? After some time, definitely they will enter into the neighboring location, so that at the center, when you sample the TB, sample the signal at TB, you will get the sum of both the signals, right? So same thing is going to happen whenever you do this with the 0 0 alpha, right? 0 0 may be represented as minus a, but you can see that right after some time, right, there will be the signal's energy will go into the neighboring locations, neighboring bits. So because of that, once again, I have at TB, that is at the center, when you try to sample, it will be sum of both of them, right? More than one, more than minus one, because both will be minus one. Let us say 75% reduction happened, right, because of the amplitude. But you see 0.75 plus 0.75 will become minus 1.5. It's a negative point. So we apply that logic over here. So if you have two successive pulses, P of t and P of t minus Tp, and right, they are positive. Both of them are positive means what happens to the sample value? It is 1 plus 1. We assume that there is no change. Let's say. Okay, just signal entered into the neighboring thing. So 1 plus 1 becomes equal to 2, right? Very similarly, if they are both are negative, P of t, current one, and P of t minus Tb, the past bit, right? If you think they are negative, right? The sample value that is going to be considered at t equal to Tb will be negative. So minus 2 is written, right? And there is a third chance, both of them being one positive, one negative, right? Complement of each other. If that is the case, right, opposite polarity means the sum will be equal to 0. One is positive, next one will be negative, right? At the same time, you can have the reverse, right? First one is negative, second one being positive. So add them up to get 0. So, right, we'll try to build a logic now. The logic says, right, if the sample value is positive, in the sense I'm directly looking at what I got at t equal to t. So if I get the value here and the value is positive, that means it should be sum of the two positive numbers, right? So that's what the present and the past bits are positive, in the sense they are ones, right? So that's the point number one, right? At the same time, let's go to the same sample, right, at TB, and I find that this sample is negative. So whenever that is negative, the present and the previous bits are zeros. Whenever they are 0, they have negative amplitude, say minus a, so you got a minus 2 answer, right? And we go to the third case. So this is something like, right, the sample value is 0. When I sample at a t equal to tb, I get a 0. So which means they have to be complement of each other. So you see, the logic says that the present and the past bit, they are complements. If this is 1, that will be 0. If this is 0, that is 1. So now what we do, we try to incorporate this logic into a coding scheme that is called as a correlative coding. Ultimately, I'm trying to allow some sort of ISI, right? Okay, so one technique is referred to as the duo-binary signal. Okay, in the duo-binary signaling, the input sequence, which is BK, right, series of numbers 10100011 and whatever, okay, that comes in, and I have to add them with the delay, because you see, our logic says that I get a present symbol and the past symbol getting added. So there is a summer block. That summer has two inputs. One input is a direct input, which is the current symbol, current bit, and there is a delay bit, TB. So you take an input, make it, you provide a delay of TB to that bit, and after the delay, you give it at the output. So you see, whatever directly comes into the summer, right, and the delay that is come after a delay of TB, they will get added. So current symbol and the pass symbol gets added over here in the summer block. So this whole the concept, whether you add a summer and a delay element all together, that is called as a geobinary conversion filter. That filter output is given to the channel because after this coding, you try to send it to the space, right? So that will carry the signal all the way from the source to the destination, or the transfer for the transmitter to the receiver. And on the receiver side, you can see that once you receive it, you try to sample it out. So you will sample the signal. Okay, all right. Once the sampling is done, right? So you remember the sampling is also being to be carried out at every t equal to integer multiple of TB, right? Just to get the proper gap between the samples and uniform sampling. Okay, and whatever you get at the output is denoted as CK. But anyway, it's ideal channel, so ideal channel will not alter your sequence. So right now, the this particular ideal channel block, what we have written, right, that has no significance because it is not altering anything. Right, there is a transfer function, but normally it will pass whatever is given as the input will go at the output. So you don't have to worry about this ideal channel at all. Okay, now let's try to give an equation now. So anyway, ideal channel has nothing to do. I just have to write an equation just before the ideal channel to get the sequence. That itself is the CK, right? Whatever comes after, whatever CK you get at the output of this summer block, right? That itself is passed to the outputs. So you can see the output equation can be written in this fashion. CK is equal to BK plus BK minus 1, where BK is the current bit. BK minus 1 is one symbol previous to this. Okay, right. So this whole concept is called as the geobinary signal. Right. Now you see, we always have to assume a value, right? Plus a minus a. So we may, just for simplicity, we try to assume that as plus and minus 1. Okay, there is a minus 1 and a plus 1. Right. Minus 1 for 0, plus 1, or 1 indicates plus 1 works. So this is how the whole encoding scheme works. So BK is there, which is the first row, that is 0, 0, 1, 1, 0, 1, 0, 0. When I try to send this, right, on the receiver side also, I should get the same thing. That's what is the output sequence, which is the last row. Anyway, we'll come to that. So normally, whenever you get a input binary sequence, you need to convert that into the polar format, because we are following the that polar form. Just before this, we wrote that okay, we are going to follow this. 0 is minus 1, 1 is a plus 1. So we'll do that conversion in the second step. This is step number 2. Okay, minus 1 minus 1 plus 1 plus 1 minus 1 plus 1 minus minus 1 and plus 1. So corresponding to every 0, you write a minus 1. Wherever you see a 1, that will be replaced as a plus 1, polar format. And then you apply the equation. Every CK needs to be addition of the current and the past. So for the first minus 1, I don't have its past. So I don't write anything for that because, right, we cannot do any assumption over that. Right after that, for the second one, we'll do with the first one. So add the, no, we don't do that, right? Whatever is there initially, we'll write. We'll start from the initial one, we take, right, add it with the second one, and then write the answer below the second one. Okay, so I write a sorry, I write this minus 2 here after adding the plus ones which is above, right? These two minus ones are added. So below this, I'm not writing anything because I don't know what is the previous one of this, right? So if you add any random thing, it will cause error. Okay, so we just don't want to do. So like that, you add minus 1 minus 1, get a minus 2, minus 1 plus 1 equals 0, plus 1 plus 1 is plus 2, plus 1 minus 1 is 0, and so on. Right? Completely fill that. So that CK is what is the duo binary signal. Right. Now you see, I need to decode this because I want to come back to the original signal. right? So there is a bk minus 1, right? Whatever was your polar format, you write it over there, and the ck value, from the ck you subtract. So this is minus 2, minus of minus 1, so that becomes plus 1, so you get an answer as minus 1. So 0 minus 1 is plus 0 minus minus 1 is plus 1, 2 minus 1 is 1, 0 minus 1 is 1, right? And so on. You can fill the fourth row like see, this is something like always on the receiver side, you we are going to get an approximated value of what has been sent. So what is sent is bk, right? Just to denote that, just to indicate that what I am calculating here is the approximated value, right? So normally you see, if the approximation is correct, you will definitely get your original signal. In this case, you see the next line, you get the original signal back, which indicates that whatever is the approximation we have done so far, right, that is working perfectly, right? So that's why we try to denote it as a bk cap. Okay, so only that's the reason. Hmm. ck is the previous line, whatever is written inside the red. Okay, that is ck. So bk minus 1, anyway, I'm going to get only from here the second minus 1, what we see here, right? So only that is the one which I'm able to calculate. The one before that, I need to, what you call, I need to assume, right? Like from the previous bk, the polar bk, whatever we have written, I'm directly writing that. Okay, so that's how I'm able to write this bk cap. So once the bk cap is calculated, simply do the, this is in the polar format, convert it back. Every minus 1 will be a 0, and every plus 1 will remain as a 1. So if you compare, right, the first bk and this output sequence, they are same. That means, yes, your duo binary is working fine. Okay, right. So the same thing I think I have explained here, right? That's fine. Now we need to look at the frequency domain analysis of this. What exactly is going to happen on the frequency side whenever you allow certain amount of the ISI, right? For a current bit, the previous bit is current bit and the previous bits are added together to get a new sample, right? Like a plus a is 2a, minus a minus a is minus 2a, and plus a and minus a is 0. So this is what we did so far. So we try to analyze the same thing in the frequency domain. Okay, so let's say the frequency response of the delay element is this. So this is again coming from our Fourier representation called the time shift, right? So whenever, right, I try to give a delay, or I want to shift the signal by TB unit, that is unit delay in this case, right? Normally, in case of the signals and system, what we studied was delay was by 1 unit, like T minus 1. But in this case, it is not 1, it is 1 TB. That's all. Okay, so you see the equation changes in this way. So inside the red, this thing, you can see that, right? What is the property being used? This is called as a time shift property of a Fourier representation. X of t has some x of f. If you shift this by providing a delay of TB units, you get x of t minus TB. So the result becomes x of f e to the power minus j 2 pi f into TB. So that is the equation. Right. So now you see there is one component that is a delay. So we are talking about the block diagram of the duo binary signal. So initially you see there is one delay and one direct connection which comes to the summer. Right. So the next sentence is the frequency response of two channels should get added to get the result of the summer block. So what are the two channels? One channel is directly giving you this one. Second channel gives you this e to the power minus j 2 pi f into t. So total response should be 1 plus e to the power minus j 2 pi f t because the Fourier representation is linear. You can add. Okay, so because of that, I'm allowed to add here. I'm allowed to perform this operation only because the transform Fourier representation is a linear function. You can apply that, right? So using that, now you see we'll write the total system. So total transfer function or overall transfer function can be written as h of f equal to, it is 1 plus e to the power minus j 2 pi f t b into hc of f. So again, as of now, the hc of f is ideal, right? But whenever you change it, that hc of f will come here and you can multiply. So we are trying to make this discussion as general as possible, right? So right now we have used hc of f, which is ideal. So look at the next line. So ideal channel hc of f is equal to 1. So below that we have written the graph as well. Okay, it varies from minus b naught to plus b naught, and its magnitude is 1. Other than that, in the sense more than b naught or less than b naught, whenever the frequency lies in this range, the value is equal to 0. So same thing we have written in the equation number 2. H of f, hc of f is equal to, this is 1, magnitude of f is less than b naught, and this is equal to 0 whenever magnitude is greater than b naught. Magnitude on f, yeah. So we have answered. Let's see. Let's remove the magnitude for the time being. Then I need to write two lines over there, right? One is that only, so for whenever it is 1, I can directly write minus b naught less than f less than b naught. Is it right? So I can eliminate that two conditions into a single condition if I put a magnitude. Magnitude means remove the negative. Even if your frequency is between 0 and minus b naught, okay, in the sense the frequency is somewhere here, let's assume, you see this point, okay, whenever the frequency is over there, right, if you take a magnitude, what happens, it becomes a value which is between 0 and b naught. So that's what I have written here, right? So 1 when magnitude of f is less than b naught, neglect the negative sign. So it may be between 0 to minus b naught or 0 to plus b naught, but magnitude is definitely between 0 and b naught, right? No, not on b naught. Okay, b naught is its value, right? The f can take minus values as well as plus value. That the meaning is this: the f can be negative and f can be positive, but its magnitude is should be less than b naught. So indicating that minus b naught greater than minus b naught till 0, or starting from 0 till plus b naught. Anywhere within this region, the value is 1. That's what is true, right? From the graph. Look at the other thing. Now, if at all I don't use the magnitude f here, I have to write two conditions. What are the two conditions for 0? F is lesser than minus b naught, and next case is f is greater than b naught. Two cases. But if you take a magnitude, right, magnitude of f greater than minus b naught will be some value greater than b naught. That's all, right? So I can directly club them together to write a magnitude f greater than b naught. That's all. Is it clear why we are using the magnitude? All right. So here the B naught is considered as the bandwidth, right? So it's a low pass signal. 0 to B naught will be the total bandwidth. Okay. Now we'll try to substitute this value of 2 in the equation 1, right? So that means I'm going to get the h of f in the following format. Only whenever the hc of f is 1, right, you get the h of f. Otherwise, it is 0, right? So the same condition we apply, magnitude f is lesser than or equal to b naught. This is the value, 1 plus e to the power minus j 2 pi f t b. Otherwise, if magnitude of f is greater than this thing, it is equal to 0. That is the h of f. Right. Now we'll substitute one property that is from the trigonometry, right, is 1 plus e to the minus j 2 theta can be written as 2 times e to the j theta cos theta. Okay, this is a one property. So directly substitute that. So theta looks like the, wherever, when I compare this, theta is pi ftb, right? So in the equation, I have 2 times pi ftb. So that's a 2 theta verb. Okay, so what I can rewrite now, 2 times e to the power minus j pi f tb into cos of pi s tb. This is when magnitude of f is lesser than or equal to b naught. And this is going to be 0 whenever the magnitude of f is greater than b naught. Okay, right. Once we have this, now we'll look at what are the various possible representations so that I can further simplify and understand what is this. So I know that from the basics of maybe Fourier transform, Fourier representation, Fourier series, or even the DFT, which is coming from the uh, DSP. Okay, DFT, discrete Fourier transform, we studied in digital signal processing. We know that the representation, whenever you take a signal to frequency domain, it becomes complex, right? So this h of f is complex means you have two options. One is to write in the polar format, alpha plus or minus j beta, my mistake. This is nothing but the real and the imaginary plot, which you can plot over there, right? We have one option like this. And another option is you can try to write as r e to the power plus or minus j theta, right? That is called as a polar format. First one is rectangular format. Now what we are writing is a polar format. In such case, if you want to visualize, you have to use a magnitude plot and a phase plot separately. So always the complex representation are written in two different plots. I cannot use a single plot for that. That's what we studied earlier. And also we know that what are the two different plots, either real and imaginary plot separately, or magnitude versus the magnitude plot and the phase plot. Okay, right. Now what I try to uh, do here, let me check what is the format of this h of f, what we have written. This looks like 2 times e to the minus j theta cos of pi f db. So 2 and cos pi f db looks like a magnitude form. That's r. And if you have a e to the power plus or minus j theta, that is a phase plot. I have, yes, right? So here I can see that I have 2 times e to the minus j pi f tb. So that is a e to the minus j theta. That's a phase format. So I have to write two graphs now, one for the magnitude, one for phase, right? So magnitude means take that r and take its magnitude. So magnitude of h of f is 2 times magnitude of cos function. So since the cos function can take positive and negative, right? The negative value will get converted into positive now. Okay, because of the magnitude. So whenever the magnitude of f is lesser than or equal to b naught, this is 2 times the cos of pi f db. So actually I can do this easily at whenever I see that it is 0, it is magnitude is highest, cos 0 is highest, cos 0 is 1. There is a outside I am multiplying by 2, right? So 2 times that one. So you see the magnitude of this is 2, highest is 2, and until b naught it should come down, right? So it will reach 0 at b naught as well as minus b naught. So cos function is a even function, in the sense on the whatever you have on the left side of the y-axis should be there on the right hand side. Okay, so that's why we get this kind of graph. This is the magnitude response. Okay, this is the magnitude response of the h of f. Similarly, I can also try to write the phase response. So phase response, in the sense you see what is the theta and simply plot the theta versus the frequency. That's what you can see here. Theta of f, that is minus pi f tb. Magnitude of f is lesser than or equal to b naught. It is 0 for f greater than b naught. So simply substitute all the values, right? So at 0, f is 0, so it has to pass through 0. That's what I understand. At minus b naught, it will become minus pi by 2, and at plus b naught, it becomes plus pi by 2. Okay, so since the slope is negative, this has to be a decreasing straight line, not increasing. Okay, so we could identify that, okay, this is how the h of f gets plotted, right? Both the graphs we could get. Since it is complex, one magnitude plot and one phase plot. All right. Okay. Then let me try to get the impulse response. Impulse response is normally denoted as h of t. If you have a h of f, which is a frequency domain term, take its inverse for Fourier representation, inverse Fourier transform to be specific. right? Whenever you take that, you will be allowed to come back to the h of t. Okay, you are allowed to come back to the time domain. That time domain representation itself is called as the impulse response. So impulse response is inverse Fourier transform of h of f. But what is h of f? Frequency response. So in words, if you want to remember that, you can note there. Impulse response is nothing but the inverse Fourier transform of the frequency response, h of f. Any frequency response you have, take its inverse, come back to the time domain, and that time domain equation itself will be the impulse response. Okay, fine. Now I want to calculate that impulse response of the h of f, which we have the equation readily available with us. Okay, right? So h of f into e to the power j 2 pi f t df, right? H of f is just now represented 1 plus e to the power minus j 2 pi f tb. Multiply that with the e to the power this function, which is the mandatory term to be present in any of the inverse Fourier transform. Okay, now we just have to split. Okay, we'll multiply and get the term. So when you multiply, you get e to the power j 2 pi f t here plus e to the power j 2 pi f into t minus tb, because the term containing tb has a negative sign. Then simply we can integrate e to the j pi 2 pi f t by j 2 pi t minus b naught to plus b naught, e to the j 2 pi f t minus tb over j 2 pi f tb b minus b naught to plus b naught. Okay, substitute the limits. Whenever it is b naught, it is positive. Whenever it is minus b naught, the term becomes negative. Okay, so you can see here, you get e to the power j 2 pi b naught t minus e to the power minus j 2 pi b naught into t whole divided by j 2 pi. So the both the terms, I can see a sine function over there because of this rule. If you have a e to the power j theta minus e to the power minus j theta by 2j is equal to a sine theta. So I can see that e to the j theta minus e to the minus j theta as well as the 2j in the denominator, both the terms. So I can simply rewrite that as a sine function. I just have to see what is the theta value. Theta value in the first term is 2 pi b naught t. The same theta value in the second term is 2 pi b naught t minus t. So sine theta by theta is a sinc function, right? So it gets converted into the following format. Okay, sinc of t by tb plus sinc of t minus tb by t. All right, so that's the format which you can directly write as the answer. Okay, right. Then, fine. So actually, for that reason, you can see here I have substituted. Capital B naught is what I substituted, which is 1 by 2 TB. So when you substitute, the terms get cancelled, and whatever is the remaining term, or remaining term itself is sinc function. Okay, sine theta by some theta. Okay, so that's why we write like this. Okay, so this equation, which has two sinc functions, is the impulse response. Now we'll try to plot the impulse response. So impulse, the black dotted is for sinc of t by tb, and the blue colored one is actually shifted version of that, sinc of t minus tb by t. I'm adding them together to get the red colored one. Okay, so we can see that until here and until here it's same, right? On both the sides it will follow the right, the what do you call, the red and blue will be followed. At the center it is sum of them, so you get a more value, you get a larger value over here. Okay, at 2 TB it becomes it. So once it is positive on one side, it will go to the negative until the next complete cycle, that is 2 TB to 3 TB it is below, then 3 TB to 4 TB above, then 4 TB onwards below, and so on. Same thing you copy on the other side. Minus TB to minus 2 TB it is negative, minus 2 TB to minus 3 TB positive, and so on. Okay, so this is the h of t, right? Whatever we had so far, right, that h of f, it is, if you see in the time domain, this is how it look like. So whatever we considered earlier, right, is true now. You see, originally sent signal was where, from 0 to 2 TB, correct? Because 0 to TB was 1, TB to 2 TB was another one, correct? We had two ones, But now you see after some time, right, they are spreading out now. So you see, right, signal has gone out of the bounds, correct? So it is not perfectly square, it is some other shape. So what is that shape? It is sync function. Two individual sync functions clubbed together to get a different function. That's what is this. Okay. So by just performing the bk plus bk minus 1 to get a ck, right? Everything whatever we discussed so far is justified, right, by this h of t. Okay, so to get this h of t, first we need to find out the h of f, which is the Fourier representation. From there, you take the inverse to come back to h of t, and h of t justifies whatever you assumed earlier. We told that, okay, we are considering two ones. We started from there. And now you see, yes, two ones are visible here. At TB, if you sample, you get a positive value, indicating that there are two positive numbers. Present and the past sequence is, right? Present and the past sequence is 1, 1. So it's positive, means they are both are ones. We can come to that conclusion if you use this sample and if you sample this. Okay. All right. Now let's discuss about the problem with this. There is a major issue with this that is called as a error propagation. Okay. Error propagation in the sense one of the bit becomes a zero, right? If one of the bit is assumed as zero, then the problem arises wherein, right, you will not be able to correct the problem at all because all the samples after that error will become erroneous. You have, this is what is called as error propagation. One of the bit becomes so one of the decision is in error, means all the other sample, all the following samples will be in error. Okay, right. So that is the concept called error propagation. We'll see. We consider the same bk, right, which is what you can see in the first row here. Then we convert into polar, that's also same. Then we get a ck, which is bk plus bk minus 1. It's the same value like our previous problem, previous example. But now you see what happens. I assume this error bit, one which is I'm supposed to take it as a minus 1. Let me assume that that itself is, I make an error. I just want to show the error propagation. So first bit itself is in error. Do the same calculation we did earlier, right? You see that the error propagates. One of the bit is in error, all the other bits followed by that bit will be in error. Minus 1. So minus 3. Right? Anyway, minus 3 is not in our whole list, right? So that means it is error. So after that, everything will be in error. That's all. So that's what is called as the error propagation. So error propagation is the major drawback of this. That's why you see in the first block diagram, we assumed ideal channel. Ideal channel means there is no error. Okay, so for a purpose, they assumed ideal channel initially, saying that if at all it is practical channel, then this is what is going to happen. The practical channel will definitely make errors. Okay, it will change the current symbol into some other symbol before it is received by the receiver. So if that happens, definitely there is they cannot show that what is this duo binary signal, right? So for that reason, they assumed a ideal channel so far. But now it is no more ideal, it is a practical channel because of which you have an error. So whenever the error happens, right, all the other received samples will be with error in this case. Okay, now how to overcome that? So you can overcome the issue of error propagation by uh, before you apply the duo binary coding, right? You add a pre-coder to that, right? As the name suggests, before the doing something, you apply the pre-code. Okay, so what is pre-coding? Take a take a bk, which is the incoming signal, and you have to perform a modulo to addition with the delayed version of your answer. Okay, you get a ak as an answer. Delayed ak, you add it to the bk. So do this. That's called as a pre-coder block. and followed by the precoder block, right? You do the same steps, whatever we did earlier. So it's a modulo 2, which is nothing but the XOR operation. We normally call it as XOR operations in our the logic design or digital circuits. So let's see now. So this is the equation. AK is equal to BK XORed with AK minus 1. Right. So let's see, right? If BK is equal to 0, right? BK is equal to 0 means any symbol is 0, the output will be plus 2 because you are adding two ones over there. And if the BK is equal to 1, right? BK is equal to, whenever the input is 1, the output CK becomes equal to 0. This is what is going to happen over here. Okay, in our the circuit, the final output will be like this. And how do you detect that? Simply pass it through a rectifier. Minus becomes a plus. Rectifier is going to do that, right? And put it into a threshold value, right? Normally threshold could be a 0 value or something. Okay, right. Now you see. So we come to the same calculation. PK is there. Do a pre-coding. Pre-coding requires one previous sample. Let's assume it as 0. Okay, so 0. So always do this calculation. So whenever the inputs are same, output will be 0. Like 0 plus 0 is a 0. 0 plus 0 is a 0. 0 plus 1 is 1. 1 plus 1 is 0. Right? Whenever same thing is added, you get a 1, 0. Okay, right. So 0 plus 1, 0 is 0. 0 plus 1 is 1. 0. Like that you add. Then whatever is the pre-coded value you have, right, that is AK, you convert into polar. That's what is our first step in the duo binary signal, right? So convert that and send. So after that, that's a polar value. So get back your CK, right? CK is equal to AK and AK minus 1. Simply add the two values in AK to get the CK. So minus 1, minus 1, minus 2, right? So like that. Let me assume there is an error here. So the second bit is in error now. You see, I'm expecting minus 1, minus 2. But let me say because of the channel, there is an error. Okay, the second value which I highlighted, right, as an error, this should have been minus 1, minus 1. So minus 2 was there. This is expected to be minus 2. But as you know, yeah, we take it as 0 because I wanted to introduce an error. If at all this was the normal duo binary, I know that that will propagate, right? This should have been causing all the next values with error. But now you see what happens. You are not dependent on the CK value, but you depend on the polar AK value. So minus 1 plus 1, 0, minus 1 minus plus 1 minus 1, 0, and all the values are actually calculated from the polar AK, right? So whenever you actually receive this, you convert this back, you see other samples still remain same. Okay, so original PK, whatever you send, it's there. So error is not going to propagate here. Okay, error propagation is going to stop in case of this modified duo binary signal. Negative value will be 0. Anything more than 0 will be 1. That's what is a rectifier. Okay, you see the block diagram. CK is there. Pass it through a rectifier and a threshold. Okay, rectifier means anything lesser than 0 will be 0. Okay, anything more than 0 or 0 is a positive answer. Okay, like that. 0 is 1. Anything more 0 or more than 0 is 1. It is 0. Okay, so again, you see there is a threshold coming into picture. So it's actually taking a magnitude, correct? I'll go back once again. I'll go back. You see here, CK is there. I'll take a rectifier, right? That is magnitude, then a threshold. Threshold is given something, maybe it is closer to 1 in this case. So anything more than 1, magnitude is taken more than 1, means it is 0, right? Less than 1 is 1, magnitude. Okay. So less than 1 means 0 comes over there. So that will be coded as 1. Right. So like this we do this. Okay. You have any doubt? I can explain it if you want. It's okay. All right, let's proceed. So the same thing I have given in the statement, right? If there is error for one bit, it is not going to affect the other sequences or other bits in the sequence. So there is no error propagation in this case. All right, fine. Then we have the next concept that is called as M-array baseband band. So far whatever we considered is a binary. So two values. So M-array means M different levels. So pretty much similar concept, right? You have a pulse generator. Whatever is given as input will be generated by, will be converted into a pulse format, right? But that pulse format depends upon how many levels you want. That's all. Okay. So in the input sequence, how many bits are converted into a single symbol? Depending on that, you try to generate the number of levels over here, right? Other than that, everything is same. You have a transmitting filter, channel h of f, receiving filter, sampling, apply to some logic device. We compare it with the threshold and get the output. Okay, that still remains same. But what changes here is the number of levels. So previously I used to send either 0 or 1 separately. So that's what a binary communication means. But now you see you have an option to club two neighboring bits. You can say 0 0 is my one symbol, 0 1 is the other one, 1 0 is the third one, and 1 1 is the fourth one. So now you see I have four levels, which means the output of uh, the pulse, right? The pulse generating circuit should have four levels, right? So previously plus A for 1, minus A for 0. That was our convention, right? But now you see I need four different levels. That's all. So how do you generate the four levels? We'll see an equation now. Below that we have an equation. So similarly, take an example of 3 bits at a time. Symbol contains 3 bits, 0 0 0 0 0 1 up to 1 1. Okay, right. So m is equal to 8 array. Right. Now you see, let's try to give an example first. If at all you have four levels, you can do, right? You can apply the levels like this. 0 0 gets the least one, minus 3 volts. 0 1 is minus 1 volt. 1 0 is plus 1 volt. 1 1 is 3 volts. You see equal spacing between the points, right? So right, we expect that, right? We cannot give it at random, right? Or varying lengths or varying separation is not usually justified. Okay, right. Similarly, just take an example of binary where we used to write plus a and minus a, which were equally distant from the origin, which is at the center. So same thing is what we are looking now. Okay, so something like this we are expecting. Now we'll write an equation to perform this operation. Okay, equation comes later. Let's see. So the amplitude level at the pulse generator output corresponds to different symbol. Yes, we understood that. So if you have capital T as a symbol duration, 1 by T will be the signaling rate. How quickly you can change your symbols. That's what is a symbol signaling rate. So again, we have the same equation. X of t is k minus infinity to plus infinity a k into g of t minus kt. So here the g of t minus kt is what we are talking about now. Okay, so that is what we are trying to write it in this way. Okay, all right. Now, so let us look at what is this AK stands for. All right, so this particular AK value, which you can see here, a value can be anything, right? So AK is equal to discrete, which are the discrete levels. How do you assume? Depends upon whether the number of the M values are even or odd. So I have given an example on the right side, which you can see, right? So that is, right now it is assume the 0 is a central one. So I have odd numbers means 0 will also be one of the level. Okay, 0 plus 2a and minus 2, right? Considering 3, m is equal to 3, which is odd. So look at the second line of the AK equation. If at all m is equal to 5, there will be two more values at plus 4a and minus 4a. So totally they are 5. So whenever m is odd, 0 is also included. Just remember that. Okay. And whenever the m is even, the 0 level is not included. Okay. So it's like the first line of the equation, plus or minus a, plus or minus 3a, plus or minus 5a, and so on. So we have taken example of m being equal to 4. So plus a, minus a, plus 3a, and minus 3a. So those are the 4 levels. Are you okay? As per this requirement, it's here. Okay. Now we go for an example, right? Consider a 4 array system and try to draw its waveform, right, for the sequence 0 1 1 1 0 0 1 0. So club from the left, you try to club 2 2 at a time, like 0 0 1 1 0 0 1 0. Right, this can be any other format also. You may get a 8 array waveform to be plotted, okay, where you have 8 different levels. So just look at the m value, decide what are the levels. Okay, so starting from the lowest number, you start giving the levels like this, like 0. You can see here minus 3a, I have written 0 0 near that. In the sense, if I get a 0 0, that will be the level. Then 0 1 for minus a, 1 0 for a, 1 1 for 3a. Okay, so wherever you have minus a, right, when I get a minus, so my first symbol is 0 1, corresponds to minus a. Next I have 1 1, that is 3a, right? So just draw those levels and keep connecting to form a waveform. Is it okay? If it is 8, then you have starting from this minus a plus a, minus 3a plus 3a, minus 5a plus a. Yeah, and when you club, you get 3 different bits. Like 0 1 1 will be the first bit. Then the next, sorry, first symbol. Then the second symbol will be 1 0 0. So, but when they ask 8-bit, sufficiently large number of bits are also given. Okay, you will not left out with. In this case, you see I am left out with 1 0. I don't know what is after that. So it will not be that case if they are asking a 8 array. Properly 3 3 3 3. How many groups you want? Proper number of bits will be provided. Okay, so like that you draw this, right? Every level will be corresponding to 3 bit at a time. Okay, so that's what is a m array uh, PAM systems.